All right, so if you recall, the probability is just the ratio of the desired outcome over all possible outcomes. So when you're looking for the probability of this point being contained in the shaded region, that's going to equal the ratio of the shaded region itself to the total, or the shaded area, to the total possible area. And if you look at these in a visual manner, the visual manner, the shaded area is found by taking your square and subtracting the circle from it. And then the total area, the unshaded and shaded combined, are simply going to be the outer figure itself, which is a square. Okay, so we can even connect these into a formula-based equation. If our square area is s squared, our circle is pi r squared, again our square is s squared. Here's the equation that you can use, or the formula you can use to find the probability that the point will be in the shaded region. Okay, so you have a couple options right here. And my recommendation would be just plug in a point, or plug in a number. It doesn't matter what you choose. Use something that's easy to use. If I were doing this, I would probably use just the value 1 for the radius. If 1 is our radius, what does that mean this whole side is going to be? 2. So these are the measures I'd use. I plug in 2 for S, and I plug in 1 for R. And now, I'll come back and I'll show you. This is going to appear here in a moment. I'll show you how you can do it if you wanted to use R to keep it as an unknown. So if we just use R for the radius, then our whole side would be 2R. I'm going to show you how it's done here, but then I'll also show you why I would have just used the 1 and 2 to start with. Okay, so if I plug in these values for S, the side length is 2R. So if I plug that in, 2R quantity squared minus pi times R squared, and I divide that by 2R quantity squared. If I expand this out, I square the 2, square the R, pi R squared stays as it is, and do the same thing down below, square the 2 and the R. Well, in the numerator here, I can remove a common factor of R squared, and that leaves 4 minus pi. In the denominator, it stays 4 pi R squared. And what you're going to see right here is these R squared factors cancel, and I'm left with exactly what I would have gotten if I'd have just left this 1 and 2 here. So that's why I would have just used the 1 and the 2. I would have come to this value right here, which I could then calculate if I took 4 minus pi, took that quantity and divided by 4. I'm going to put a decimal in here so it displays as a decimal, and I get my probability to be approximately 0.2146. And remember, probability is going to be a value between 0 and 1. 0 meaning it's never going to happen with certainty, and 1 meaning it's going to happen every time with certainty. So it winds up kind of corresponding to percentages if you move the decimal 2 places to the right. So there's a 21.46% chance that a random point picked on this figure is going to fall in the shaded region. Okay. Now, what if instead of asking you the probability question, what if I asked you find the area, or find the shaded area, if the circumference of this circle were given as 6 pi? If I had actually given you a number and asked you to calculate it, really the setup would be very, very similar to this. The shaded area itself is the square minus the circle, which would be s squared minus pi r squared. Okay, and so if you looked here, if the circumference was 6 pi, what would the radius actually be? Or actually, if you knew the circumference was 6 pi, what would be the measure that's easiest to calculate? Circumference is d pi, so if d pi is equal to 6 pi, then that means the diameter is 6. If the diameter was 6, this whole length is 6, the radius is going to be 3. And so if I plug those values in here, I plug in a 6 for S and a 3 for R, I get my answer, 36 minus 9 pi. Again, it's an area, so it's square units if you were labeling. And that would be the exact answer. You could calculate the decimal form using your calculator if you wanted to, but that's the exact answer.